Okay, thank you. Thank you for the introduction, and thank you once more for coming back to the final lecture. So I just wanted to write up the basic summary of what happened over the last two lectures. So as before, we're going to fix a normal subcritical rule. So this was something that determined our class of equations that we were able to solve. This, together with the dimension of our base space, were the ingredients necessary to construct a model space or regularity structure. Model space is being the more correct term. From this, we were also able to build a positive Hopf algebra, which contained all trees that every single branch of those trees from the root was positive. And then we saw how to construct a coproduct on the space, as well as a comodule for, well, how to turn T into a comodule for T plus. Maybe at this point I should mention that something I didn't emphasize before, but for people familiar with branch rough paths or Butcher series, you might have noticed similarity actually between this delta plus and the Connes-Kreimer coproduct. So this similarity is not at all a coincidence, and it appears exactly for the same reason here as it does in numerical analysis, actually. So the fact that it appears in quantum field theory with the work of Connes-Kreimer is perhaps, I don't know, maybe a coincidence, maybe not, but that certainly you can make the relationship with numerical analysis precise. Then finally, we looked at these maps capital pi, which satisfied these properties. And from yesterday, you might notice I dropped one of the properties, which is multiplicativity over the tau and the sigma. So if I enforce that pi is multiplicative, so pi of tau x is equal to pi of tau times pi of x, this would completely determine what capital pi is. But without that additional assumption, we just call this map admissible. And then we can recursively construct two new guys. So we can recursively construct pi x for every point x in our base space, and a character fx. So this fx belongs to the character group of tau plus, according again to this recursive definition. This is not circular; it's an inductive definition. And we said that if pi is admissible and the model that is built from pi x and fx, so the pi x is the same, and the gamma xy's are given by this representation that we saw last time. So gamma fx inverse, gamma fy. So if that guy is a model, then we call pi a premodel. Okay, so then that's where we finished last time. So as I said today, I'm going to introduce another Hopf algebra and another character group, which is going to act on pre-models and on models. So just to motivate it a little bit, the trouble with working with when pi was multiplicative, this is called the canonical lift. It's sort of you just assign to every tree the naive function that comes from associating to every symbol the natural associated function or convolution kernel. The trouble with working with capital pi is that so often it's perfectly fine. So for example, if you're working in rough paths, this canonical lift will typically converge. And you need to use some stochastic analysis. But if psi is a one-dimensional white noise and you mollify it, then you're going to converge, this object will, as you remove the mollification, will converge to something called the Stratonovich, or a canonical rough path lift of the noise psi. So it's perfectly fine to work with the canonical lift in certain situations, and you need to use some stochastic analysis to show convergence in the space of models. I haven't talked about the topology in the space of models, but there's a perfectly well-defined one. In multidimensional situations, the case is usually different, and the canonical lifts typically fail to converge. So this is perhaps where we deviate the most from rough path theory. And this new character group, which is going to be called G minus, so for negative renormalization, is a mechanism of perturbing our model. So it's most simply described on pre-models, which is why we make the definition here. So it acts on pre-models, and it acts in such a way that you perturb the associated model in kind of a sufficiently rich manner that you can find elements of G minus that help you converge. And a distinction perhaps that we can make right away between G plus and G minus is that, so just so that you keep it in mind, so this f of x heavily depended on the realization of the noise xi. So I give you a realization of the noise xi, and say I choose to work with a canonical model, and then this fx is given deterministically after that by this. I didn't care what the law of xi was. I just built this character. In the case of G minus, this will be the opposite. So it's not going to care about typically the elements of G minus that we choose to apply to models. It's not going to be pathwise. It's only going to depend on the law of your realization of your noise. It's kind of, they live on quite different spectrums. Okay, so let's see how to define this. So define T minus to be the space of all trees which strongly conform to the rule, such that their degree is negative and tau is not planted. So tau isn't equal to IP of sigma for any P and D, and sigma which strongly conforms to our rule. Yeah. Okay. Then we're going to look at the set of forests generated by these trees. But this is the collection of all products. I call this this dot the forest product. And what it does is it just puts the two trees together, and it's commutative, so I don't care about the order. So here n is bigger than or equal to 0, and each tau I belongs to this minus space. And it's important to perhaps note that this is canonically isomorphic to n T minus. Okay, so then F minus is then the span of minus. And this is an algebra with unit, which I'm going to call the empty set, the empty forest. So I think of these guys as multi-sets of negative forests, and so this is the unit. So notice that this is different from the unit that appeared in T plus, which was the single forest, which was the forest with a single node. So this is a different algebraic structure. And then I'm going to call G minus to be the character group, the character space so far of F minus. So these are all functions that are F maps, it's linear from F minus into R, and it behaves multiplicatively. And F of the empty set is equal to 1. Okay, so that sets up our space. Then we're going to define an associated coproduct. So we'll first define it as a comodule. So, and for tree tau, and this is the first time I'm going to use the notation that I actually introduced in the second lecture. So recall that a tree tau is a rooted decorated forest. So the n and the e are to the two decorations. So I'll also write this as n and e like this. So n goes from the set of nodes into nd, and e goes from the set of edges into the set of edge types. Okay, so for tau of this type, delta minus of, I'll write it as t and e. Okay, I'm going to write out a horrible expression. Don't think too hard about this expression at the moment. I just want to have it here for reference, and I'll describe what things actually mean. Okay, so here pi minus, so okay, so this is expression. This is just a combinatorial factor, don't worry about that. Here, this is a big forest. I'm abusing notation a little bit. I said I would write a tree here, but this is actually a forest. And this is its node decorations, and this is its edge decorations. So to define the forest, this is just the kind of the natural map from the set of forests into f minus, where this is just n to all trees. So in principle, I could have extracted. Okay, so I haven't actually defined what A is. A runs over all subforests, subgraphs of T. And if I extract a subgraph that has positive degree, or somehow if I extract a subgraph and one of the components of the subgraph has positive degree, then I kill the term. I only want to see things in f minus over here. NA runs over all the nodes inside of A into ND, and EA runs over the following set. The set of all functions from partial AT into ND, where this is defined to be the set of all edges, which are in T, but not in A, and such that X is smaller than or equal to Y, and X is in A. And okay, so X being smaller than or equal to Y means that X is on path from Y to root. Okay. So in every tree, every node has a unique path that goes to the root. And if X happens to be on the unique path from Y to the root, then I say X is smaller than or equal to Y. So this gives a partial ordering on the set of nodes in a tree. NA runs over the set of all functions. Sorry, N. Yeah, this is so this is just supposed to be N of A. So N of A is just the set of nodes in A. Yeah, it's nothing to do with natural numbers. Okay, so I have to still define. So this. Okay, there was this term pi of EA, So this is a node decoration, and it's equal to all E, which are xy, inside of ET for EA of E. I'm going to draw a picture in a second, so if some of this isn't making sense, then wait until then. And then the final thing that I have to define is what is this RA of T, and also what the node decorations are. So this is most easily done through a picture. So let's look at an example. So this is my tree T, and suppose that the guys that I extract are this. So the subgraph A is this and this. Then what happens is the corresponding term in the sum becomes this. Dotted with tensor this tree. So so this is what happens combinatorially. So we contract this each of the connected components of A to a point, and so the points become. So if this is, maybe I'll put this in orange, and this one in green. Okay. So this is the contracted component here, and this is the other contracted component. So that's what R of A looks like. RAT, sorry. So this is R A of T. And suppose that my original graph had a polynomial decoration x to the k here, and say x to the n here. And then remember, I have the sum over the n's in the definition of delta minus. So I can put basically, so the sum will go over all x to the m here as well, and also over here, but let me ignore that for now. So m can be anything smaller than or equal to k. So I can't put more into A than I originally had over here. And the polynomial decoration associated with this guy will become x to the, so I sum up everything that I had in the previous connected component, and I subtract what I removed. And just as a final, maybe a clarification, so just to clarify what that boundary, so it's called the boundary of A inside of T, so this is the boundary of A, the single edge. This is the boundary of A inside of T. So in particular, these other two edges are not, because they point in the wrong directions. Okay, so this is the definition. So are there any questions actually about maybe the mechanism of how this definition? Yes. So yes, sorry, maybe I didn't make this clear. Yeah, this single tree is RA of T, and this is the A component. Yeah, so this is A. This is A. So it's this tensored with this tree, and of course there will be a associated combinatorial factor, which I'm ignoring for this purpose. Okay, so you might want to study the properties of this delta minus map, and you might like to actually show that that it's actually well defined. So the reason that it's not completely obvious that it's well defined is because it's not really clear that, so I've contracted this tree here. So the question is, do I actually still stay inside of T? And the remark or the disclaimer is that this is, you'll have a hard time if I said this is an exercise. Disclaimer, this is not true. So delta minus is not well defined. As it stands. So because in principle you might have delta minus will go from kind of T into T into F minus tensor some bigger kind of space over here. So you might need to include some extra trees that appear from these contractions. And so the essentially the reason that it doesn't always map you back into T is because we're missing an assumption on our rule. So there's an assumption that you can place in the rule, which is called completeness. Okay, so the definition of completeness is a bit technical to state, but essentially its whole purpose is to ensure that that you end up back in the space T. So actually, this maybe at this point I can even make an example, sort of foreshadowing renormalisation. So recall that in yesterday's talk by Pavel, he had an interesting renormalisation, which was of this type. Plus C epsilon u plus C tilde I epsilon partial I of u. So, so if you look at the phi-4 equation, our usual example, then depending on the irregularity of the noise, or okay, I prefer not to add fractional powers to the Laplacian, but I can tune the strength of the noise. And if my noise is sufficiently irregular, if I'm sufficiently close to the critical regime, then actually, and I don't mollify my noise in some sort of a nice symmetric way, then actually the renormalization counter terms you end up with depend on the derivative of u. Which is a bit surprising because you might recall that this is just a polynomial equation inside of u. So my natural rule knew nothing about derivatives of my kernels. And this is a manifestation of the fact that the rule that I gave you for the phi-4 equation was not complete. So it's not closed under this. If I apply this delta minus, I'm going to end up with a tree that sees a derivative. So this is now an exercise that I can set. So so as an exercise, try to find this tree. Show R is not complete for 543 that I gave before, but just do it by showing that by using this remark and showing that delta minus doesn't map you back into T. Yes. Yes. Mm-hmm. Yes. Yes. Exactly. Yes. 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 So this is, so okay, at this stage, the fact that the delta minus might not map you back into t on the right factor is, I guess, a purely algebraic fact. So in some sense, it's not about the approximations of the noise. Actually, I mean, even if psi is Gaussian, it's just, so actually these terms appear whether your multiplier is symmetric or not under reflections. So yeah, it can appear for a variety of reasons somehow. So in practice, you would want to work with a complete rule if you were to use this theory, basically. Yeah, I don't know if that answers your question. Yeah, this term, like whether you take if you take a symmetric modifier, then just you can choose to set these constants to 0. Yeah, and otherwise you can't choose to set them to 0. But maybe I can clarify a bit later. Yeah. Right. So then a very similar definition for delta minus will also map you from, okay. So a very similar definition, delta minus, can map you from t minus, which was the span of the negative trees, into f minus tensor t minus, where I essentially just, so I add, all that I would do is I would add a projection onto the negative trees. Okay, I can't. So I would just add a projection onto the negative trees when I contract my when I contract t, and then I extend it to the whole of f minus. So f minus, if you just look at its definition, it's freely generated by the span of the negative trees. And so I can extend this multiplicatively into f minus tensor f minus. Okay. And it turns out that this is very similar to the result holds as we had before. So f minus to f, there exists a map f minus to f minus called the antipode, such that f minus dot delta minus a minus is a Hopf algebra. And T is a comodule over f minus. So comodule in exactly the same sense as we had before for the delta plus. So okay, so we have a very similar construction as we had for delta plus. So now the main kind of theorem about how this all interacts with the models. So this is one of the, I guess, the main results in Lorenzo's paper, is suppose you have a pre-model. So let me just write it. So if capital pi is a pre-model, then so is ig This pi g is defined by, in a very simple way. So you take, I gave the G minus spaces here. It's the character space of F minus. Delta minus. Then so this is pi g is also a pre-model for all g and g minus. And the map which sends, let me write it like this. So if I look at the model generated by pi, then I map it to the model of pi g, this is continuous. We always want to have continuous mappings in this business. It's very important. You might kind of wonder how does this, is this map really defined? Because what if I have two different pi's that have the same models? Then maybe these guys will be different. So is this actually a well-defined map? So it's not very difficult to convince yourself actually that the information that you have about capital pi is the same information that you have about the pi x together with the characters. So this model is able to completely recover the capital pi and vice versa. So Z is a bijective map. So this is the statement makes sense. In fact, the only reason that we work with models rather than this capital pi is because there's no nice way to define the topology of models using capital pi. The most natural way to define topology of models is with these guys. But this renormalisation map is most easily described in terms of capital pi. Okay, so so how might one try to so for the rest of the lecture, I want to give a sketch proof of this result. So it's helpful. So sketch proof. So it's helpful to extend delta minus one more, to define delta minus once more by going from t plus to f minus tensor t plus. Essentially, as before, we put an appropriate projection onto. Actually, no, you don't even need to put a projection here. So you define it for these guys as above, as over there. And then after this, we extend it by multiplicativity. So this delta minus will be multiplicative over t plus. So t plus was an algebra. And notice that if I picked actually an arbitrary tree in t plus, so an arbitrary tree in t plus has lots of edges coming out of the root, and I applied the formula above to this tree directly, then that doesn't coincide with and kind of got the appropriate tensors of forests and trees. That doesn't coincide with the definition I just gave. It almost coincides. But notice that here we can never extract because we exclude basically planted trees from the space from the t minus space. So remember, there was this final condition that we don't include planted trees. We never actually extract if we ever see a tree with a single node. So this is tau, and this is I of k. Then we'll never actually extract the root, because if I extract a subgraph of this containing the root, I'm automatically going to see a planted tree. And so here, when I look at a generic tree inside of T plus, I'm never going to extract the root either, because I'm basically just going to look at extracting subgraphs individually inside of these guys. So I'm never going to be able to extract something like this, for instance. I'm not allowed to do that. So in this statement, I'm not actually requiring continuity. It's a consequence of the. Why am I interested? Why is it important? Right. Yeah. So I didn't specify the topology. So there's a topology on the space of models that you can just define. So the point of the topology on models is that all of these analytic maps that Lorenzo was speaking about become continuous with respect to this topology on the space of models. And this is very important because you might want to be able to, for example, you take approximations of your noise, you renormalize them somehow appropriately with this some g. Typically, you would have like a g epsilon in here, so you would have a epsilon dependent character that you renormalize your model with, and you want to the kind of your ultimate goal is to show that solutions to these renormalized PDEs of this type converge to some sort of a limit. This is very important. You want to show that they converge to a limit. So if you can show that you break up the argument into two steps. You first of all, a purely deterministic step, you show that this PDE is actually a continuous function of the model. This is a purely deterministic. I give you one model, and then I can solve this PDE. And I set up the topology on my space of models in a very careful way that this becomes continuous. And then, of course, if I want to show that these guys actually converge, then the point of I'm left to show that my models converge to a limiting model. Okay. Yeah. So I'm not sure if you will actually speak about the topology on models. If you're obliged to, yes. Let's talk outside after. Right. So then you can show that T plus is again a co-module over F minus. So this delta minus defined in this slightly different way from above gives you a nice action of coaction of delta minus of F minus on T plus. And then so okay, I have 20 minutes. I think that should be. Hopefully enough time. Okay, so let's denote by I gx fgx for x and Rd. The kind of the I'll write it as in quotation, the model for pi of g. So pi of g is another map of the type that I just rubbed out. And so I can construct iteratively this pi gx and fgx. What is very helpful, so as part of the helpful statement that, that I said over there, it turns out that proving continuity of this map and the fact that it defines a pre-model boils down to proving the following identity. So a very simple identity. And this identity mimics how I defined pi of g. So g minus acts very simply on pre-models, and I would like it to act just as simply on the pi x's and these fx's. So the topology that I keep speaking about that I haven't written down, it's most naturally defined in terms of pi x and in terms of these fx's, or the associated gammas. So having such a clean relationship is extremely kind of helpful in proving this, the fact that this is actually going to be a model, and the map is continuous. And in turn, this is implied by the following identity. The identity we've seen actually several times in some of the other talks. It's not too hard to see that that this identity will follow from this one. And actually, in my so I can leave this as an exercise actually, or even spell out the argument in the lecture notes. Where this okay, I haven't told you what M13 is. M13 takes a tensor ABCD and maps it to A dot C tensor B tensor D. So you can boil down this statement about models to a purely algebraic statement. So here there's no pi's appearing anymore at all. The purely algebraic statement in terms of the T plus, T, and F minus. So I hope it's not too unbelievable that this is you would want to have this. So the unfortunate fact, so this is called co-interaction. So this is studied by like similar situation been studied by Kurush and Dominic. So you kind of have these two Hopf algebras. They're both acting they both have a co-module space. So this T. And you want to show that they're somehow don't live in totally different universes. You want to show that they actually kind of act in a nice way together. So this would, for example, imply very nice identities like, if it would imply identities like M of G gamma F is equal to mg gamma fg. Like, so where m of g is equal to g tensor identity delta minus, and gamma f is sort of the same except identity tensor f delta plus. So it's, I already defined the gamma f before. So this co-interaction property would apply kind of like a very nice nice identity like this, a bit like an equivariant equivariant function or something like this. Okay, so the trouble with this, and what I want to explain in the last 10 minutes or so, is that this identity is not true. So it's not true. So I want to give an explicit example, which hopefully won't take up much time, but I think it's very, very instructive to see this example because it also suggests exactly what you need to do to fix it. Consider the following tree. So sigma squared is this big tree over here. And I pick my scaling so that sigma of s is in between, say, -3/2 and 1, -1. So sigma squared is in between -3 and -2. And my scaling for I is equal to 2. And just pick it to 2 because that's the number I'm familiar with. So then you compute what happens on the left-hand side. Well, tau is a negative tree. So because so this would imply together that that tau has negative homogeneity. So if I go back to my definition for delta plus, this guy is just tau tensor 1. This is very simple. So this left-hand side is going to be M13 delta minus tensor delta minus of tau tensor 1. And in turn, this is quite easy to see that this is just delta minus of tau tensor 1. Okay. Now let me compute what delta minus of tau is. This is equal to, and this is maybe a good way to see how this delta minus map works. So I can extract the empty forest. I can always do this. And then I extract all non-planted negative subtrees. This gives you sigma squared, and then it's going to give you a tree like this over here. And so this tree can be written symbolically as I of 1. Right. So what you can see is then if you compute delta minus tau and ID tensor delta plus first, then this is going to be tensor delta plus of empty set tensor tau plus sigma squared tensor this guy. And if you compare this expression, this is the delta minus of t, and here I have delta minus of t. And so if the co-interaction property were true, these two expressions should be equal. But that would imply that delta plus of omega should be equal to omega tensor 1 for this can be omega and this can be omega. So for both of these choices of omega, for these two trees, I need to have this identity. But what turns out is that this delta plus, so if you look at, and that's true for tau, I wrote that above, but for this guy, if you look at the definition of, so this is equal to I of 1, and so I of 1 has scaling 2. So I of 1, this tree, has scaling 2. So what you're going to see is that you're going to see this guy, so I of 1 tensor 1, and then you're going to add on polynomials of some degree smaller than 2. This will be x to the k over k factorial, and then some non-trivial terms here. So specifically I of k of 1. So this fact that you have this delta plus and hitting something which is now of positive degree is where this co-interaction property breaks. The problem is that I extracted a delta minus from tau. So delta minus extracted a tree from tau, this sigma squared, which had a very negative degree. By doing so, I increased the degree of tau, and this didn't interact very nicely with the fact that delta plus was defined as kind of having these sums of polynomials whose degree was at most this the degree of this tree here. So it's the fact that kind of by extracting a negative subtree, I increased the degree of tau, but I really shouldn't have. So the delta plus shouldn't somehow extract out these polynomials. This was just an artifact of my previous definition. So the nice idea behind how to fix this is to leave behind. So the idea how to fix this is to leave behind some extra decorations. Which, remember, essentially the degree of S. So the degree of the extracted trees at the nodes. So essentially what's going to happen is that you will you'll have kind of a new space of trees. So you effectively redefine everything I did before. Except my trees now are going to be of the following type. So I'm going to have an N and an O and an E. So I write this as T, N, E. T, N, O, E, where O is a function from a set of nodes inside of T into the real numbers. And in fact, I could even make this this set of negative numbers, non-positive numbers. And this delta minus map is now going to so the way delta minus and the delta plus change is the delta minus of a tree is going to behave exactly like we did before. So this double sum is going to have the same exact node and edge decorations, but this extra decoration gets extracted whenever I extract a tree, and this RA of T, and I add a new I add a new node decoration at these edges, which basically sums up. So if I had a tree like this, I extracted out these trees here. This was the connected components of my tree. Then I would, in my contracted tree, I would leave behind essentially this extended decoration at this root would be the size of the total kind of scaling of A1 here. This. So that's what these extra decorations will do. Okay. And then inside the definition for delta plus, so you would define as a very similar delta plus map, except, so here I'll write this as I of 1. So instead of putting the scaling here, I'll put a new scaling. So this would be the definition of this extended coproduct, where delta, where this dot plus is the same scaling as I had before, but plus the sum over all the degrees of these extra decorations that I had at the nodes. Okay. And so yeah, so this does exactly what I said. It kind of remembers the degrees of the trees. I think this the remark that this helps was I think it was essentially Ivan's observation in his thesis. And then I think so then let me just present the main result of just run out of board space. So then what I think the main, actually the main algebraic result in this paper, from which this result on the models essentially follows as a corollary. So it's quite a consequence of this, is that delta plus x and delta minus x co-interact. Okay, and so after this, if you set everything up on this new larger structure, on this new extended regularity structure, you get these identities above, provided that everything has these extended decorations, and then you prove this theorem for this. You prove the theorem over here for this extended structure. Then you can effectively go back down to the to the original structure in a canonical way. So let me just maybe apologize in particular to Kurush. There was pre-Lie algebras in the title of the talk. I have cut these out due to time constraints. But let me just say a couple of words. So the kind of the picture that that one should keep in mind for I am very conscious of the time, but I think this is a very nice picture. Okay, so you have some space where your noise lives. So this is the kind of the overall picture that I wanted to draw. Then you have equations. And so you have these maps. So M here is the space of models. What we've done is we've lifted our noise to the space of models, and we showed that there was a very large, well, sufficiently large group of which acts on these models. This was this G minus space. And and what turns out is that so this is now in some sense a commutative diagram. So and it's a commutative diagram in the following sense. So if I lift up my noise to model space, and I look at this sol A, so A is this is the solution map, sometimes called the abstract, and this of G. So if I look at so F here is my nonlinearity. This is what comes to me in my original equation. So this is F lives in here. F is in here, and here. It's kind of like a correspondence between these guys, but there's no real arrows. Then, so I lift up my equation. So the way I would actually solve an SPD in practice is I would lift up my equation to the space of these model distributions that we briefly saw yesterday. And then I solve, so this abstract solution map is continuous. Then I reconstruct it. And the way that this relates to my original problem is that I have, so there's a concrete solution map, if you like. This is the solution map that is, well, classical, I should rather say. This is the solution map just to a deterministic PDE, so given a realization of psi. And I should just put psi here. And what happens is you have this, so I act on my models with some element G, and what I need to do is I need to act on my nonlinearities with G in order to make this equation true. So what ends up happening is that you end up having an extra group, an extra action of G minus, essentially on the space of nonlinearities. So this is roughly how the picture works. So it's really in that final step where kind of really algebras appear for the reason they appear in numerical analysis too. Okay. Right, yeah, like say +2 or something. Yeah, and this is the reconstruction map, yeah. Okay, yes, thank you.
The fact that you can take the character of renormalisation at the level of the pre-model instead of the model itself, so that in particular it doesn't depend on how you recentered. Is that a reasonable assumption in general? Does that depend on stationarity of the noise, or?
So the fact that I chose for G minus to act on my pre-models this way. Yes. Yeah, yeah. So no, this wouldn't work. This wouldn't work in general. Yeah, it's a good question. So in general, if your noise is not stationary, there's no reason for these counter terms that appear in your equation to be constants. So they themselves might depend on the covariance of your noise, which if it changes with space, it'll be a function as well. So I think it doesn't. So what I would expect to change is that this G would somehow be now space dependent, but I wouldn't necessarily need to care about the re-anchoring. Like the re-anchoring mechanism shouldn't I think affect this part. Yeah, but the G minus space would now be characters with values and functions.
EVA, which I know because I'm going to discuss it next week, which solves this where they have a sort of, they have it on the level of the kernel, but they exactly have this problem that they have renormalization function. And they changed the way they introduce a notion of preparation maps, and they solve this solves this problem. The only thing which they haven't solved yet is the convergence of the model, I think. But there's some way to, just by chance I know it because
there's actually, there's a different way to deconstruct this renormalization group, this is the G minus. In fact, it stops, you make it larger, and there's a recursive way of kind of doing it, and I think it stops even being a group when you do that, but it's still sufficiently rich, it contains your previous ones. And the recursive structure, from what I understand, helps you actually prove things. So they can prove this, what Tom was saying, actually without needing even extended decorations. So.
Plantedness assumption. I understand that you don't want the planted tree because you don't have a product at the root, so therefore you don't need to renormalize. But what is somehow not so clear to me, maybe it's obvious, but at least not to me, is if you could have a tree, so if you have a planted tree and the tree that you add this integration at, it could still be negative, right?
Yes.
So I'm somehow a bit puzzled why this the plantedness is ruled out. I mean, you don't have a product at the root, but you could have up.
Yes, but I think the philosophy is that if you already know how to renormalize the tree sitting above the root, then integrating it doesn't cause any extra renormalization considerations. Yeah. In fact, you could even rule out more things, like you could even rule out polynomial decorations at the root, if you wanted to. Yeah, I'm not actually sure why in your paper you didn't rule out that, Lorenzo, but why did you rule out plantedness but not that? And so, but I think it's to some extent an arbitrary choice. Yeah.